Hello and welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. These are guided notes number 19 in the series on section 4.1, Sequences of Numbers. So before we begin, let's ask, what is a sequence? If I have a set of elements A, then a sequence is going to assign the numbers 1, 2, 3, 4, and so on to elements from A. A1, A2, A3, A4, and so on. We notice that it's an ordered list, number one, and number two, these elements might in fact repeat. We don't have any requirement that they are distinct elements of A. Now for this class, we're going to be mainly focused where A is the real numbers, but one could consider sequences in general. Very much like a function to A, whose domain is the positive integers 1, 2, 3, and so on. I'm going to write the positive integers this way. I know your homework defines this to be the set of natural numbers. This is also called the set of whole numbers. And sometimes this set, z plus, confusingly enough, is used to include 0 here. I will be treating the natural numbers, written n, as the set of non-negative integers. I consider the natural numbers to be the cardinalities of finite sets. It's how many siblings I'm allowed to have. It's how many oranges I can have before I start cutting up the oranges. Now, since I think it's totally fine for someone to have 0 of something, I think that having 0 be a possible count of a number of things is a very reasonable thing to do. Of course, we start counting on 1. If someone asked you to begin counting, you probably wouldn't say 0, 1, 2. You would just start at 1. And so I understand that the natural numbers, as I have defined them, is not such a great set for sequences unless we want to begin with a sub 0. This is a reasonable thing to do, to define n as being the set of positive integers. Your homework defines it this way, and other reasonable mathematicians, and it uses that to define a sequence. I would prefer to keep my definition. We all have our preferences. But in any case, a sequence is very much like a function, but our domain has been restricted. We are no longer considering a real number line's worth of inputs. We're just considering 1, 2, 3, and so on, and asking, what is the value at that point? Now for us, these values will be numbers, but other than that, we have very few constraints on them. We absolutely could define sequences in this way, where we start counting at 0 with the 0th element, but it leads to some bit of unnaturalness, and when we talk about the first element, it's not a sub 1. So I'll keep to their definition of using the positive integers, 1, 2, 3, and so on, as our domain. But, it really wouldn't hurt things too bad. Your first element would just be A0, and that would mean the 7th element would be A6, which is where things get a little confusing, but I think it's pretty mild. And this is, in fact, a real issue in computer science, because in computer science, some lists will start counting their first element as 1, but others will count it as 0. And you just have to be aware of these things. Now, I'll also say a little bit about set notation. Sometimes we use these braces in order to indicate that we're talking about a whole set of things and not really just one element from a sequence. A sequence has an infinite number of elements, one for each positive whole number. And using braces, we kind of distinguish that from a single element of the sequence. This is a little bit of abusive notation, though, because a sequence isn't really a set of elements. It's ordered, number one, and number two, elements are allowed to repeat. So if anything, it's a countably infinite ordered multiset. But we're not going to talk about the set theory of sequences. I'll just say that I prefer this little additional notation, which lets me know that I'm talking about something a little bit different than a set when I'm talking about a sequence. Let's actually start here. One main skill we need to have is how to evaluate a sequence given its sort of function definition. And really that's just replacing n with one of these positive whole numbers. If I do that and evaluate the arithmetic, I get the following. So a1 would be minus 2, a2 would be a half, and so on. The next example involves this exclamation mark called factorial, and we evaluate n factorial as follows. If we're talking about 0 factorial, that will be 1. And if we're talking about any larger positive whole number, that will be that whole number times the factorial of what came before. This is called a recursive definition, where I tell you how to evaluate something based on what happened earlier. Now, some of you might know this factorial definition already as a descending product. Let's see if these two definitions sync up. Well, we are given that 0 factorial is 1. 1 factorial would then be itself times 0 factorial, 1 times 1. 2 factorial would be 2 times 1 factorial, which was 1. So this is 2. 3 factorial would be 3 times 2 factorial, which is 2. And now we get a 6. 4 times 3 factorial is going to be 4 times 6. That's 24. And 5, well, you can see this is 5 times 24 is 124. Let's note that that is the same as the descending product. 5 times 4 times 3 times 2 times 1 times 1. We want the extra 0 factorial term in here. Usually we just omit these. You really only have to multiply all the way down to 2 because these are not going to change the output. As a little bit of practice, they ask for us to find 11 factorial. That would be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3, and so on down to times 3 times 2. There is also a button on the calculator for that. I would type 11 into the main screen and then go to Math, over to Prob, and down to the exclamation mark. As such. So now let's look at an example that has a factorial in it. All we're going to do is replace n with the positive integers. So that's 1, which gives us 1 over 18. 2, which gives us 2 over 30, or 1/15. 3, so we get a 6 up top. And 9 plus 3 more 9s, 36. Plus 8 is 44, and reducing we get 3/22. Likewise for a to the 4th, we're just doing 4 factorial, which is 24 over 4 squared plus 9 times 4 plus 8, which is going to wind up giving us 24 over 60, 2/5 when we reduce. Number 5 asks us to find a formula for a general sequence. This is sometimes a very tricky problem. What you're going to want to do is develop a way of describing what's happening as we go from one element of the sequence to the next. Find out what's staying the same, what's changing, and how is it changing. Here we can see something staying the same. We have fractions in each case, and the numerator is a 9. The denominator goes from 4 to 16 to 64 to 256 to 1024, and so on. And what we can see is that we are multiplying by 4 each time. That makes this denominator 4 to the 1, this one 4 to the 2, 4 to the 3, and so on. That means the nth term of this series is going to have a 9 still in the numerator and 4 to the n in the denominator. And so we have a general expression for this sequence. For number 6, we notice that we have fractions in each position, 1's up top, but actually the signs of the fractions are changing from positive to negative to positive to negative. So one thing you can do to write that changing of signs down as a rule is use powers of -1, because the even powers of -1 are 1 and the odd powers are -1. So this can be used to alter my signs. I just need to put n even up here when it needs to be positive and n odd up here when it needs to be negative. And just going up by 1 each time will back and forth us between even and odd. So what we want to do is start this one on a positive. That means I'm going to have a even power of -1 to begin with. That is to say, at the first element, this should maybe be a 0. So if we put n minus 1 here, this first element will have a 0th power and turn this into a 1. A positive 1 is desired. Now, what about the denominator? Well, the denominator is increasing by 1 each time. 3 to 4 to 5 to 6 to 7 to 8. So we can see this first one as being 2 plus 1, then 2 plus 2, then 2 plus 3, then 2 plus 4, then 2 plus 5. And I would write it like this because I want to see how it's changing with respect to this case. The first element is going to be a 1 for my n in this variable expression. So I want this to be a 3, then a 4, then a 5, then a 6. It's going up by 1 each time. But if I write this first element in terms of what plus 1, it'll be a 2 plus 1. And that lets us know that we want to start this as a 2, because the first element, a sub 1, will put a plus 1 down here, giving me a 3. Then 4, then 5, then 6, as we increase n with our alternation of sign taken care of by this upper term. Now we're going to look at some recursively defined sequences. These are sequences defined in terms of what came before. You want to know what the next element is? Take the element before and add 6 to it. And that is going to begin with a 5. We take 5, that's our first element, and then add 6 to it to get the next element, which is 11. Add 6 to that to get the next, which is 17, and so on and so forth. What we might notice here is that each element can be written as some multiple of 11 plus 5, and then add no 11s, then 1 11, then 2 11s, then 3 11s, and 4 11s, and so on. So notice we're adding, to get the nth term, we're adding 1 fewer 11. So this would be our first term plus n minus 1 times that 11. And in general, This 11 here would be any number we like, called the common difference. That's because the difference between subsequent elements is equal to d. Here we have something similar, except we're using multiplication to get our next element by timesing the last element by 9 each time. So we start with a 4, and then the next one is gotten by timesing by 9. 4 times 9 is 36, and so on, and so on, and so forth. Now, notice that, similar to what we're doing last time, instead of adding some multiple of d's, we are now multiplying by some exponent of r's, where this r is called the common ratio, because the ratio of any term to the previous term will be r. Here we have a recursive formula based on two previous terms, the one that came before and the one that came before that. So notice they need to give us two starting points here. A1 is 3, A2 is 4, and then we know that the next one, A3, is going to be the sum of the two that came before, which gives us 7. Then A4 is the sum of A3 plus A2, that is 7 plus 4, which is 11, and so on. A partial sum will be a sum of a finite number of elements from a sequence. Now, oftentimes when written like this, we want a sequential selection of elements from the sequence. That is to say, we want one, then the next, and so on, all the way up to some other one. That's written this way using what we call sigma notation. This is uppercase Greek S, or sigma. We want to start from the nth element and count adding up all the way to the nth element. If we start at 1 in the special case, that would look like summing up the first n elements of the sequence. So let's see what that would look like in an evaluation sense. Here we're going from 2 up to 4. So we want to plug in 2 for I, then 3, then 4 into this expression, and then add up all the elements. That looks like taking this expression and changing I with a 2, then adding to that I with a 3, then adding to that I with a 4. Of course, adding a negative is the same as a difference, and if I add up all these differences, I get the following. This first one becomes 3/2, then this one minus 3/4, then this one 3/8, and summing those, we get 9/8. For this one, I'm going from the third element to the fifth of the sequence of elements that looks like 2 to the I minus 1 for its a sub ith element. So if I plug in 3 here, then 4, then 5, then add up all of those terms, I get 4 plus 8 plus 6, which is 28. Here I'm asked to add up 6 from 1 to 33. Well, there's not even a k here to substitute these k indices into. So what are they really asking for? Well, they're asking us to add 6 when k is 1. Okay, there's no k here, that's fine. We add 6 to what? Well, another 6, and then another, and another, and another, and we do that 33 times. So 33 times adding 6 to itself is what we mean by multiplication, 6 times 33, which gives us 198. And this bespeaks a formula. Perhaps we should look at some formula for sequences. So there's some rules that we should keep in mind when dealing with summations. The first is linearity, which is sort of the big kid's distributive property. It says, look, I don't care how many sums or differences you have. I don't care what constants you're multiplying by. You're always allowed to pull out constants, and you're always allowed to distribute the summation across addition and subtraction. So if I see sums or differences of various terms, I can separate those terms in different summations. Also, I can pull out constants, which are multiplying by each term in my summation. We also have a special kind of associativity, again reapplied here for the sequences. And it says if I'm summing up n elements, and let's for a brief moment say n is greater than 1, then we're going, and if we have an m somewhere between them, then I can sum from I equals m these elements of the sequence, and then continue on at m plus 1, and then add them up until I get to n again. This is sort of like doing the whole summation of one element to n elements in two different parts. We first sum to m, then we go from m plus 1 to n. This will actually be useful later on in the following sense. When we sum from 1 to n, we are first summing from 1 to m minus 1, and then from m up to n. This is just moving the plus 1 from here over as a minus 1 to here. But here I have a sum from m to n, where m might be bigger than 1. Many of our next formula are going to require that we start at 1 in order for the formula to work. But here we have a way of expressing a sum between any two terms in terms of sums that start at 1, to which the formulas will apply. So which formulas am I talking about? Well, first we saw the sum of constants. If I sum from 1 to n of a constant c, that's basically c times 1. So I'm adding 1 to itself n times and then multiplying by c. Well, I hope we see that this is just n, and so this is just n times c. The sum of the first n integers is given as follows. And as a small justification here, if I take the numbers from 1, summing them all the way up to n, I could first make pairs of them, which have size n plus 1, for each pair that I could combine. And how many pairs would there be? There would be n over 2 of them. Hence, the sum would be as follows. Now, that's not a full proof. Really, we need to break this into odd and even cases, but the formula does work. I'll leave it to you to consider the odd and even cases for this. And here we have two more interesting formula, the sum of squares and the sum of cubes. The sum of squares formula looks a little bit like the sum of the first integers, only we have an additional 2n plus 1 term and we're dividing by 6 and not 2. But the sum of the cubes looks very familiar. That's just the sum of the first n integers squared. But that seems to tell us that the sum of n cubes is the same as the sum up to n squared. So let's get back into how we might use such a thing. We could, first of all, factor out this 4 by linearity, and then take the sum from 1 to 27 of k using the formula for the sum of the first 27 integers. That gives us 27 times 28 over 2 times 4, which gives us 1512. For this one, we could again use linearity to separate, and then rewrite this in terms of their formula. The sum of 14 sevens is 14 times 7, and the sum of the first 14 cubes is 14 times 15 over 2 squared. This gives us 11,123. Finally, for this last one, we could pull out the 2 by linearity and look at the sum of the first 28 squares. Only wait a minute, we're not really looking at the sum of the first 28 of them, we're only starting at 6. This is where we might want to rewrite things as the sum of the first 28 of them minus the sum of the first 5 of them, because that'll knock out all except 6 to 28. So we could plug in for these formula as such into the sum of squares formula, because now we're starting at 1. And so when we do that, we get 7,712 minus 55 times 2, and this gives us 15,318. I should note there is a way that we could do some problems like this in the calculator. We first need to store these elements into the calculator. Let's consider 14 first. If we go to Second, List, and over to Ops, we can go down to Sequence. Clicking on Sequence, we can type in an expression such as x cubed plus 7. The variable we're using is x. We want to start with 1 and go up to 14. We can even select our step size here as 1, while it is usually fixed with our notation as we're currently using it. If I paste this onto the main screen and press enter, it will give me that sequence of numbers represented here. 1 cubed plus 7, 2 cubed plus 7, and so on. What we want to do is sum that sequence. To do that, we can either go to Second, List, that's over to Math, and down to Sum. And now, since it's in our last called position, we can just sum the previous answer, which gives us the same answer that we got using the formula. Now also, if we know we're going to be taking a sum, we can start with that. We can say, I want to take the sum of what? Now I want to take the sum of a sequence. So let's go back to List, down to Ops, and type our new sequence. This is going to be 2 something squared. Our something is an x. We're starting with 6 now and ending with 28 with a step size of 1. Now I've pasted that into sum, so it's going to automatically take my sum for me. Alrighty, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.